Hello again. For today, the first topic that we're going to be talking about is Bayesian statistics. So we're going to take a little break from R and talk more just about what Bayesian statistics is and how it works and some of the strengths and weaknesses. So this will be more kind of a theoretical topic rather than what we did before, which is very kind of technical, dealing with R. So hopefully it will be interesting, and let's get started. Okay, so our outline for this topic is we'll briefly discuss what Bayesian statistics is, then we'll go over some of the criticisms of it, and then we'll also discuss why maybe you haven't heard of it before. So Bayesian statistics, it's actually much older than the frequentist-based statistics that you know of today. So the frequentist statistics that we're most familiar with really came about in the 1940s and 50s, whereas Bayesian statistics was developed in the 1700s, and so it predates frequentist statistics by quite a long ways. But we'll discuss why you don't hear of it that much, or why you're only starting to really recently, or why you're only starting to hear about it more recently. Okay, so what is Bayesian statistics? There's actually a number of different ways that you could define this, depending on how philosophical you're feeling. So we're actually going to redefine it a number of different ways throughout the course, and none of them will contradict each other. It's just kind of our definition of it is going to become deeper as the course goes on and as you get more and more experience with it. But at its most basic level, Bayesian statistics involves using Bayes' theorem, which is this equation here that we'll go through in a minute. And essentially, it's a way to reassign probabilities across possibilities, where the possibilities are the different hypotheses we have for our system. And so again, what we have here is what's called the Bayes equation, and we'll walk through what each of these components means. So this first part, so this is the probability of a hypothesis given the data. That's how this would be read. Remember, this is what we want, right? When we talked about our criticisms of p-values, one issue is that a p-value tells you the probability of the data given a hypothesis. But really what we're interested in is the other way around. We want to know the probability of a hypothesis given the data. Or put another way, the whole reason we collect data is to test different hypotheses. So we want to know how the probability of a certain hypothesis changes as we add data, as we collect data. So that's a very intuitive way for how science works. But again, the p-value doesn't tell you that information. But Bayesian statistics does allow you to do this, right? So it allows us to calculate the probability of a hypothesis given the data. And this is called the posterior probability. So we're going to spend a lot of time dealing with posterior probabilities as we deal with Bayesian statistics. And again, the idea here is this is what we really want in science. But you can see part of this equation is what's called the likelihood, and this is the same thing that you're probably used to calculating. So this is the probability of the data given the hypothesis. And so this goes into the Bayes equation, but it's not the only part of it, whereas this is the only part of frequentist statistics. So again, this is often called the likelihood, and again, you're probably very familiar with this, or you will be as the course goes on. But then, of course, there's two other components of Bayes' theorem here. This one, the probability of the hypothesis, this is what's called the prior probability. And what this is the probability of the hypothesis being true before you collect any data. And so this is usually the big stumbling block for Bayesian statistics. But as you'll see, it's really not an issue at all. Like some critics of Bayesian statistics think that this prior probability makes it very subjective. And to a certain extent, that's true, but you can be very comprehensive in these. And of course, there's a lot of subjectivity in frequentist statistics too. So anyway, we'll come back to that topic. And then lastly, we have the denominator here, which is just the probability of the data. What this is it's really just a normalizing constant so that all the posterior probabilities add up to 1. And so what it is it's the sum of all of the combinations of the probability of the hypothesis or the prior probabilities times the likelihood across all of the hypotheses that are being considered. And so this can take different forms. So the only thing that's changed here is the denominator. And so if you have discrete variables, this denominator is just the sum of all combinations of the prior probability and then the likelihood. But when you have continuous variables, you have to integrate over all the possibilities. And so don't worry, we're not going to be doing any calculus in this class, but this property is going to come back and, I don't know what I just did there. This issue of having to integrate over all options is going to come back a little bit later. So let's work through an example. Like that's kind of just kind of the theory of it is a little abstract. So it will make more sense if we work through an example. So let's say that we have some marbles in jars. And let's suppose that there are 2 jars. Jar 1 has 100 red marbles and 40 green marbles. And jar 2 has 40 red marbles and 80 green marbles. So let's suppose that you have a green marble, and we want to know what's the probability that it came from each jar. So we can use Bayesian statistics to answer this question. So again, here's Bayes' theorem, or Bayes' equation. And so what we want to do is calculate this posterior probability. So we have 2 hypotheses. Hypothesis 1 is that it came from jar 1. Hypothesis 2 is that it came from jar 2. And so we want to know the probability of each of those hypotheses given the data. So the first thing that we need is this prior probability. So suppose that we don't know anything about these jars yet. We want to know what's the probability that it came from either jar. Of course, if we don't know anything about the jars, it seems reasonable to assume that there's an equal probability that it came from either jar. Right? So this could be a reasonable prior probability, right? Before we know anything about the jars, there's no reason for us to suspect that it's more likely that a marble came from one jar or another. So our prior probability of our marble coming from jar 1 is 0.5, and the prior probability that it came from jar 2 is 0.5, right? So since we have 2 hypotheses, and we think it's an equal probability from either, then those prior probabilities are 0.5. Next, we need to calculate the likelihood, the probability of the data given the hypothesis. So that's what's the probability of getting a green marble under hypothesis 1. So under the hypothesis that it came from jar 1. So the probability of getting a green marble from jar 1 is just the frequency of green marbles in that jar. So it'd be 40 divided by 40 plus 100. So this is just the total number of marbles. And so the frequency of green marbles in jar 1 is 0.286. So that's our likelihood. That's the probability of the data given the hypothesis. So assuming this hypothesis is true, so assuming that it came from jar 1, the probability of getting a green marble from jar 1 is 0.286. But then we do the same thing for jar 2. So given the hypothesis that it came from jar 2, what's the probability of getting a green marble? So in this case, the frequency of green marbles is 80 divided by the total number of marbles, which is 80 plus 40, which gives us 0.667. So that's our likelihood of a green marble coming from jar 2. So now we have our prior probabilities and our likelihoods for each of our 2 hypotheses. Now we just need to calculate this denominator, which again is just the sum of all the prior times likelihood combinations that we have. And so our posterior probability of our hypothesis 1, that our marble came from jar 1, given the fact that it's green, is the prior that it came from jar 1, 0.5, times the likelihood that it came from jar 1, which is 0.286, divided by the sum of all prior times likelihood combinations. So here we have our prior times likelihood from jar 1, and here we have the prior times the likelihood that it came from jar 2, right? So we'd have as many variables here as our hypotheses. And so if we do this, we get a probability that it came from jar 1 of 0.3. That's our posterior probability. Similarly, we can do a similar calculation. So the probability that it came from jar 2, given that it's green, it's the prior that it came from jar 2 times the likelihood that it came from jar 2. Again, now the denominator is the same. So times the sum of all prior times likelihood combinations. So here's the prior and likelihood that it came from jar 1, and here's the prior and likelihood that it came from jar 2. And so if we do this math, we get a posterior probability of 0.7. So here, these are our posterior probabilities again. So this is a probability of a hypothesis given the data. So it's 0.3 and 0.7. So these are our posterior probabilities. So you might say, okay, well, big deal, right? Those are pretty similar to what we would have come up with the frequentist way, right? These posterior probabilities aren't too different from the likelihoods. And that's true in this very, very simple case. But a very important part of this is that now we have the probability of the hypothesis given the data rather than the probability of the data given the hypothesis. And this is what we want in science. And then, of course, it's not always going to be so similar. Oftentimes, the posterior probability could be quite different from the likelihood. And you can't tell from this simple example, but being able to do this opens up a whole new world for how you view data and how data supports different hypotheses. So I think now Bayesian statistics might seem kind of mechanical, right? You plug numbers into this equation. But as you get a deeper understanding of it, it's going to, I'd say, change your life more and more as you go. So let's look at this a slightly different way. So we can think of this as a table where our hypotheses are different rows. So in this case, we have 2 hypotheses, that it came from jar 1 or from jar 2. And then we have the needed data as the columns. So we need the prior probabilities and the likelihoods. And then we need the product of those for each of our hypotheses. And then we can just fill in this table, right? So here are prior probabilities that it came from each jar, each 0.5, and that sums to 1. And so all your prior probabilities always have to sum to 1. That's a characteristic of them. And then we have our likelihoods, which we calculated from the data, and there's no requirement for likelihoods to sum to 1. In fact, they almost never do. So it doesn't really matter what they sum to, but I just included that here to fill in the table. And then we just take our product, right? So 0.5 times 0.286, 0.5 times 0.667, and we can fill that in here. And then this is actually, I probably shouldn't have put this in. This is the sum of those two, right? So it's the sum of both those products. So it's not the sum of this row, it's the sum of these rows. And so then calculating this posterior is a bit more easy with this table like this because all the numbers have been summarized here. So here our posterior probability that it came from jar 1 given that it was green, is our prior times the likelihood here, 0.143, divided by the sum of all of those prior times likelihood combinations, 0.477, and then we get our 0.3. Similarly, I don't know why this navigation bar is here, but anyway, for jar 2, it's this 0.334 divided by 0.477, so that equals 0.7. All right, we'll stop here for now, but we're going to work through another example soon.